from Institute of Engineering and Technology, the Department of Electronics and Communication. Welcomes you to the session of electromagnetic field. Today we are going to discuss about the number 4, that is uniform wave propagation, with topic plane wave propagation. So let's start the session. First of all, let's see the introductory part of different type of media, that how the different media will be classified. So it will be classified into the continuous media and it is further classified into the lossless media as well as for the lossy media. So for the lossless media and lossy media, we consider three different parameters, that is sigma, that is conductivity, mu is the permeability of medium, and epsilon is permittivity of medium. Now each of them is related with the relative as well as the free space propagation model. So here if we talk about the mu, means permeability of medium, then it will depend on the free space permeability as well as for the relative permeability. So mu will be given by mu0 into mu I, while epsilon will be given by epsilon 0 into epsilon r, where epsilon 0 is free space permittivity and epsilon r is relative permittivity. Here the value of mu0 is 4 pi into 10 raised to minus 7 Henry per meter, and epsilon 0 is 8.85 into 10 raised to minus 12 Faraday per meter. So this is about the lossless medium. Please note that for the lossless media, the sigma should be below, means there should not be any conducting term. That's why the conductivity is 0. Now for the lossy media is further classified into the good dielectric and the good conductor. We will talk about the characteristic of this dielectric as well as for the conductor in unit number 5. For this unit, we have to consider the two different conditions for the good dielectric as well as for the good conductor. So for the good dielectric one, the sigma is equal to 0. Obviously, dielectric means it is similar to insulator, and insulator has conductivity 0, and that's why here we found sigma equal to 0. And mu equal to mu0 into mu r, as we discussed in the previous slide, that mu is permeability of media, mu0 is free space permeability, and mu r is relative permeability. Same way for the epsilon is medium permittivity, epsilon 0 is free space permittivity, and epsilon r is relative permittivity. So for that case of good dielectric, the remaining two parts is the same, means mu and epsilon is same as we discussed in the previous slide, but the only change is in sigma, that is conductivity is 0. But if we talk about the good conductor means it has an adequate amount of sigma. So that's why we can say that sigma will not be 0. That's why sigma is not equal to 0. Remaining mu equal to mu0 into mu r, means medium permeability depends on the free space permeability as well as relative permeability, while epsilon is equal to epsilon 0, means permittivity depends only on the free space permittivity. Okay, so that is about the lossy media. There is also another case about the perfect conductor. Obviously, the perfect conductor means it has the highest amount of conductivity and lowest amount of resistivity. Means ideally it should be resistivity rho should be 0. So if rho is 0, then rho is inversely proportional to conductivity, means rho is inversely proportional to sigma. So here if rho is 0, then sigma is infinite. Mu equal to mu0 into mu r, and epsilon equal to. Now next is uniform plane wave in free space. So this is one figure in which we show the E field and H field. So if you see in this figure here, E field and H field components are perpendicular to each other, means E dot H equal to 0. If we want to form the Helmholtz equation from this, then del square E, this is the 2 times differentiation of field intensity, that is equal to mu0 epsilon 0 del square E upon del T square. We can denote this del square E by del T square by E bar double dot. We already talked about the meaning of E bar double dot. If double dot is there, then it means 2 times differentiation. If one dot is there, it means 1 time differentiation. So here del square E is mu 0 epsilon 0 del square E upon del T square, del square H is mu 0 epsilon 0 del square H upon del T square. This is two time differentiation with respect to time. Now if we want to travel this in the z direction with respect to time, then we have to differentiate the particular term with respect to z. So del square E upon del z square. If we want to do the partial differentiation with respect to y, then it will be del square E upon del y square. So each term will denote like this, like del square E upon del z square equal to mu 0 epsilon 0 del square E upon del t square. If del square E upon del y square will be written, then it will be again mu 0 epsilon 0 del square E upon del t square. But here please note that the time variant will be changing. Like if you want to do the differentiation with respect to y, then you have to write over here del square E upon del y square. If you want to do the wave travels in the x direction, then it will be del square E upon del x square. Okay. So similarly, here if we want to do the wave equation for the particular velocity, then velocity will be denoted by v. And if we talk about the free space velocity, that free space velocity is also denoted as c, and this free space speed is called as 3 into 10 raised to 8 meter per second. So it will comes from this equation v equal to 1 upon under mu 0 into epsilon 0. If you put the value of mu 0 and epsilon 0 in this equation, you get the free space speed, that is 3 into 10 raised to 8 meter per second. So one question will be asked that why in the free space the speed is 3 into 10 raised to 8 meter per second. But if the wave is traveling with respect to one medium, then it will be v equal to 1 upon mu e. Here mu and epsilon is the medium permeability and medium permeability. Here the equation is with respect to the different terms like del square E upon del t square is v square, del square E upon del z square. Same way, phase velocity. Phase velocity is basically the velocity with which the wave propagates. So velocity is 1 upon under mu 0 epsilon 0, and it is equal to 3 into 10 raised to 8 meter per second. Group velocity is velocity at which the group travels with particular amount of infinite attachment will travel will denotes the group velocity. Here it is denoted by Vg, and it is the change with respect to the phase constant, d omega upon d beta. Here intrinsic impedance. The next term intrinsic impedance is denoted as beta, and it is the ratio of E field and H field, means it is given by E upon H field. Intrinsic impedance, it is the ratio of E field and H field that is given by E upon H, and it is also the ratio of mu and epsilon. Mu and epsilon is the permeability and permittivity of medium. Here it is given by under mu epsilon ohm. So if you want to find out the intrinsic impedance for the free space, then you have to put mu 0 and epsilon 0 in place of mu and epsilon. So if you put mu 0 and epsilon 0 and take the ratio in place of mu, you have to mu 0, you have to put 4.2 10 raised to minus 7, in place of epsilon 0, you have to put 8.85 to 10 raised to minus 12. If you do that, you get the intrinsic impedance, that is 377 ohm. Now the next one is the propagation constant. Propagation constant is denoted by gamma, and it is given by the Helmholtz equation like del square E and del square H. In terms of del square E and del square H, we can write the gamma square E and gamma square H. Here gamma will denote the propagation constant, and it is further denoted in terms of attenuation constant and phase shift constant. So gamma is equal to alpha plus j beta Napier per meter. Here 1 ampere should be equal to 8.690. This is a conversion equation that one can convert it into V decimal. So now phase velocity is depend on the phase constant also. So phase constant is radian per meter, and it is given by beta equal to omega into root mu epsilon. But if you see this root mu epsilon, then 1 upon root mu epsilon is velocity. So we can write this equation in terms of velocity like beta equal to omega and upon v. One more equation related to the wavelength is denoted by the lambda. So it has a direct relation with the phase shift constant. Phase shift constant is nothing but our beta. So wave reflects after every 2 pi radian, means after every unit circle it denotes the wavelength. So lambda is equal to 2 pi upon beta. In place of lambda, because c equal to f lambda and c is free space feedback. So what happens when it is travels in a medium? So in that case the velocity is denoted as b instead of c, and that's why I write this equation lambda equal to b upon f. So let's see one example related to it, that E field in a free space is given by the equation 800 cos 10 raised to 8 t minus beta by kz volt per meter. You have to find the different quantities like phase shift constant, wavelength, field intensity at particular point at one time, that is 8. Here beta is equal to omega upon c. Omega is 10 raised to 8, c is 3 into 10 raised to 8. Here you have to compare this equation with E0 cos omega t minus beta y. So here in place of omega there is 10 raised to 8. So 10 raised to 8 upon c. So beta will be answer is 0.33 radian per meter. Lambda, now beta has a relation with wavelength, that beta equal to 2 pi by lambda, and that's why 2 pi upon beta means 2 pi upon 0.33 is nothing but 18.85 meter, that is lambda. Now for the relation from the E field and H field, that is related with the intrinsic impedance. So E by H is eta. So H equal to E by eta. We have the equation of E, and free space eta is 377 according to mu 0 upon epsilon 0. So we get the equation for the H field. The remaining terms remains as it is, 10 raised to 8t minus beta y. Unit of magnetic field intensity is ampere per meter. So this is the second quantity. Now we have to find out this H at a particular point at a particular time. So this point 1, 1.5 and 0.4 is nothing but the coordinates of Cartesian system. So whenever x, y and z appears, you have to put this point, and in place of t you have to put 8 into 10 raised to minus 9. So if you put this in the equation, you get the answer for H for a particular point. That is 2.129 kxy ampere per meter. Now let's see one another example, that E field is given 10 cos 2 pi into 10 raised to 16 minus beta z ay. You have to calculate beta and lambda. So again you have to compare this equation with the original equation of E field, that is E0 cos omega t minus beta z. So omega t is nothing but 2 pi into 10 raised to 6. Okay. But omega is equal to 2 pi f. If you compare this, you can get the equation for the f, that is 10 raised to 5 f, that is 3 into 10 raised to 8 upon 10 raised to 6. So big lambda is 300 meter. Now let's put the value of this lambda into the equation of phase shift constant, that is 2 pi by lambda. So 2 pi by lambda is 300, so 0.0 meter. Okay. So this is about the plane wave propagation and the examples related to it. Up to this, if you have any doubt or queries regarding this session, you can ask me on my email ID. In the further lecture, we will discuss about the remaining part of this chapter, that is the depth of penetration and the pointing field. Okay. Thank you for watching.